Oh, that's not
Okay, everybody, this is section 4.9, page 220. Explanation of how to do it. Here we go, folks. Last one in the section, or last one in the chapter. Not very hard. You guys are all caught up, right? Okay. All right, here we go. We are going to write polynomial functions for a set of points. That's the first thing we're going to do. You've done it before, but only for quadratics. Applying it and extending it to polynomials is not hard. We're going to write polynomial functions using finite differences. You've done finite differences before, and I think I've told you it's a dumb thing to know. But we're doing it because it'll be tested on ISAT and possibly ACT. So it's my responsibility to make sure you've at least seen it and have some chance of doing it properly on those high-stakes tests. Okay? And then we're going to use technology to find models for data sets. That's the most useful thing you'll learn, and you already know how to do it. So it's going to lead you through a few things. This won't be very hard. That doesn't mean you can zone out. Stay with me. First one is to write polynomials getting a set of points on it. If you look at example 1, please. Are you there? In example 1, they give you a picture of the graph, and you are to write its equation. And you're going, I can't do that. I could tell you, maybe if you look at it very carefully, you could say it's probably a cubed function with a negative leading coefficient. Because it starts high and ends low, right? You looking at it with me? Yeah. You could probably determine that. But as far as that goes, that's about the only thing we can expect. That's not true. Because the points they gave us were given to you strategically. The points are, 3 of the points are zeros. And then there's one additional point. Remember doing this with quadratics? We would give you certain values, especially when we were doing intercept form of a quadratic. You're going, I don't do that at all. It had to do with zeros. And then they would give you one other point to use to plug in for x and y in order to find a. Remember doing that? Just kind of recall a little bit. To do it for this one, the zeros are at -4, 0, 1, 0, and 3, 0. The zeros don't matter except that tells you they're zeros. It's the 4 and the 1 and the 3 that's going to allow me to get started writing this. The 4 came from a factor of x minus 4. No, plus 4, because it was negative. Is it -4 that it is?
Yeah.
Yeah, -4. So it came from that 0 of -4 came from a factor of x plus 4 in the equation. Is that right? What are the other two? X minus 1 and x minus 3. Okay, so y equals this, except folks, there always is this thingy in the front here that will possibly reflect it, which we expect here, right? Starts high and ends low. It will also vertically stretch or shrink it and make it give us this actual graph, not just any graph that crosses at these 3 places, but the actual graph that we're seeing. And that letter is A. We've used it before. It's A determines whether it's going to, with a quadratic, determines whether it's going to open up or down, and whether it's going to be vertically stretched. Here, it determines whether it's going to start high and end low or start low and end high, because I've got 3. It's going to turn out to be a 3rd degree. And how much it's vertically stretched. Same thing. We got to find it. We can't, because we've got 1, 2, 3 variables left. That's why they give you the 4th point. The one that they gave you here just happens to be on the y-axis, but it wouldn't have to. Could be any other point on there except for 0. Any other point will work. And the point they gave us was 0, -6. This is the additional point. So what we do is we replace, boy, this one's going to be super easy. I'm going to have you practice one that's a little tougher. What we do is we replace the y in our equation that we've written so far with -6. Well, it's not going to be that easy. And we replace all 3 of these x's with 0. So it would be 0 plus 4, 0 minus 1, 0 minus 3, which is, as you can tell, 4 times -1 times -3 times a equals -6. What's this product? 12. So I have -6 over 12 equals a, which is -1/2. Turned out negative like we expected. So what is the equation? Well, we come back up here. We rewrite this one, only we replace a with what we found it to be. We leave all the zeros there because that positions the thing in the right place on the grid. And we put x and y back in to generate all the other billions of points on it. Does that make sense? So the final answer is y equals negative 1/2 times x plus 4, x minus 1, x minus 3. And people at this point always ask, do I have to multiply that out? And the answer is only if you enjoy doing that. This is enough for me. I don't know what Big Ideas wants. Big Ideas may require you to do that. So if you do this assignment on Big Ideas and they won't accept this and they require you to FOIL it out, you may want to do it on paper because this is fine for me. I don't care what form it's in as long as it's correct. Everybody good? See how that works? Now this one was really nice because plugging in 0 just gave us these numbers. If the point had been 2, -6, then we'd have had to do the arithmetic in each one of these to get these numbers, but that shouldn't be too bad, right? Okay. I want you to look at the monitoring progress in the middle of page 220 with me, so that I'm going to help you understand what they've given you, and then I want you to try this. Okay? Because they're not going to give you a graph. They're just going to give you a set of points. Look at number 1 on monitoring progress. Which of those are zeros? Which one of those are points which are telling you where it hits the x-axis? Okay, talk to me about the first, second, third, and fourth.
First, fourth.
First, third, and fourth, which means the additional point is the 0, 10. Right? And that's just as nice as the one we got up here. They're giving you 0 for x, which is really nice. And even if we did monitoring progress number 2, which ones of those points are the zeros?
1, 2, 3.
The
First, third, and fourth. And the additional point, which is the second one that they give you, is also 0 for x. So these are nice. I want you guys to do number 1. See if you can come up with the equation where something has those 3 zeros and that extra point. Try it, like up here. If you need some help, that's why I'm standing here waiting for you to need me, so let me know. If anybody needs some scratch paper, I can dig it out real fast. Anybody need more time? What was 8? 1/4. What kind of a polynomial do you suppose it is? Cubic. We had 4 points, but only 3 of them were zeros. So it's a cubic function, and because it turned out to be a positive, we expect it to start low and end high, right? Hitting those points on the way through. This is a reminder of what we did. Okay. The next main concept is using common differences. And I don't want to actually put this one on the board because this is just a reminder of a quadratic. Would you look at the table near the bottom of page 220 where it says finite differences and then it gives you a table, X, Y, in a horizontal fashion. Y'all see it?
Mm-hmm.
Okay. What the first thing is when you're going to use this method, which I find to be fairly useless, but we're going to learn it again. First thing you have to do is decide if the x's are incremented evenly. They don't have to be 1, 2, 3, 4, 5, but they have to have the same gap in between them. So you analyze the x's, and in this case, we've got -3, -2, -1, 0, 1, 2, 3. Yep, evenly incremented. Then, once we've determined that, then we go grab those y values in the same order that the x's were in, and we start subtracting them. And when you subtract, you always take the one on the right minus the one on the left. So in the first difference there, you see 4 minus 9, and down below the little lines there, they got a negative 5. Then 1 minus 4 is negative 3, 0 minus 1 is negative 1, 1 minus 0 is 1, then 3, then 5. Y'all see where that's coming from? The blue set of numbers is called the first differences. And if all of those numbers in the first differences had been exactly the same number, doesn't matter the number, if they all are the same, you know, a linear model will work great. You need to write a line. Okay, but they weren't all the same. So we do it again. We take negative 3 minus negative 5, which is really negative 3 plus 5, that's 2. Negative 1 minus negative 3 is 2. Negative 1 minus 1 is 2, and then we get 2s all the way across. On that row, that's called the second set of differences. Since they are all the same, because 2 was how many differences we had to do, a quadratic whose degree is 2 would be the best fit for this data. Do you recall that? Yeah? Okay, so in example 2, we have another set of data. First of all, are the x's evenly incremented?
Yes.
It's pretty clear. 1, 2, 3, 4, 5, 6.
Step 1. Find the function value. Find the first difference.
Okay. Then on example, then the y values. The x's are incremented evenly. The y values are these. These I want to put on the board so that you can understand what we're going to do, and so the people that are listening to this video can know what's going on. This is example 2 for those of you referencing it, and I'm only putting the y values up here because I have already verified with everyone that the x values are evenly incremented. So the y values in the correct order are 1, 4, 10, 20, 35, 56, and what is that, 84? Okay, so those are my y values, and I'm going to try to figure out how many sets of differences it's going to take for them to arrive at the same number. So this first one is going to be 4 minus, we'll put this in colors so that doesn't work. Red, blue, oh, what's the first one? Blue, red, green. Oh, how fun.
Christmas.
Blue, we'll do blue first. Okay, so help me out here. You may need your calculator at some point. What's this difference? Is it? Is it 3 or negative 3?
It's 3.
It's 3 because it's this one minus this one. This is? Okay. 21?
28.
Okay, well, obviously they're not the same, so we gotta go again. What's this difference? Oh, this is looking good. Yeah, they're not the same, but we can certainly see what's going on here. And the next set of differences then have to be, because these were just marching on up. So this difference is? How many sets of differences did we have to do? 3. 1, 2, 3. Not the originals don't count. This is your first set of differences, second set, third set. And it took 3 to get them all to be the same. So we are going to get a third polynomial out of this. So how do we recover that polynomial that has these for points? Yes?
Is there an easier way than having to go through?
Absolutely. And this author wants you to do this. And then he says this, which I would have done at the beginning. He says, use finite differences to determine the degree of the polynomial function that fits the data. Then, use technology to find the polynomial function. I would have done that at the outset. And the cool thing is, if you use the technology, the x's don't have to be evenly incremented. Just any set of points you can get. And then when you graph them, you can look at the points that are plotted and try to figure out what kind of curve. You guys are familiar enough with curves to try to decide whether it's a cube or a quart or whatever. Now, I'm thinking we might be able to do this and still have that person who's watching it see it. Okay. So here's what we do. We made all that effort to decide that a cube fits it best, and now we're going to plot the points and make the same decision. Still, they will test you on this idea, on those crazy tests that you have to take. It's a nice thing to know. It's not really useful. Okay, so the first thing we do is plug it in. That's the first thing. Hang on. Okay, so now, if we get this thing to talk to us. Hang on. So what do you suppose we're going to do to use technology to recover this? What do you suppose the first thing is we have to do while we're waiting for this thing to come up?
We'll put into some sort of equation.
And how do we get, so this thing is thinking about the information that we've been given? Where do we start?
Don't we have to put the into?
Yeah, and that's exactly right. Where do you start with that?
Stat edit.
Stat edit, yes. We need list 1 and list 2 to be full of X's and Y's. Okay, so go back to your book and actually put the X's in. They were 1 through 7. I'll put the Y's in and go with them. Okay, does anybody remember what we do next after we've got the data in? Not yet. Next thing, we fit a window, remember? Because these numbers are kind of out of control. The X's aren't. I'm going to go from 0, because 1 was my first one. I'm going to go from 0 to 10 on my X's. But on the Y's, I'm going to go from 0 to, what was the biggest one? 84. I'm going to go from 0 to 100 by 10s. Okay, so the next thing you do is fit a window based on your X's and Y's. And then go to Y equals, erase anything that's in there not pertaining to this problem, and turn the plot on. Because you can't see the points without turning the plot on. That's what people, I put it in, I can't see it. Yeah, we'll tell it that you want to see it. Plot, and then hit graph. We get that. Now, this thing looks for all the world like a quadratic, right? When you look at this, remember you said, do we have to do this? We have to do this differences stuff? Then I said, no, you can just go straight to here. But you have to do 2 things if you're going to figure out what really fits best. This looks like the beginning of a parabola to me. And we might not be seeing all of the graph. I am not certain when I see that a parabola is going to fit it best. But here's how I test it to see. Next thing, go to stat again, over to calc, down to quad reg, because that's what I suspect it is. So hit quad reg. And if you don't have this, because my operating system's awfully old, then put the pertinent information in there. For me, it has to be list 1, comma, list 2, comma, and then your guys is the ones that have got them all listed down. You got list 1, list 2, and then it says store equation in, and you're right, you should have your cursor right there. Then we all go vars, y vars, function, y1, enter, or in your case, calculate. Y'all there? Do you all have this diagnostic R squared on?
No.
No? Okay, we'll come back to this. For those of you who have this diagnostics R squared on, just sit tight for a minute. For those of you who don't, I need you to follow these instructions absolutely, item for item. Are you ready? You go second and the number 0. We need to go to the catalog. And then we need to go to the D part of this. And the green letter D is the x to the -1 key. Do you see it? Down the left side right here. So go alpha D. Oh, I'm sorry. I already had alpha on it. Then go down to the D section until you get to diagnostics. There will be a diagnostics off and a diagnostics on. You want them to be on. So hit enter. And hit enter one more time until you see the word done. Got it? Now that everybody has that on, if you already had it on, then just leave what's on your screen there. Now that it's on, you can hit clear. Then go stat, calc, quad reg, list 1, list 2, vars, y vars, function, y1, go. Now have you got an R squared there? And does it have the same value as mine? I would be very, very happy with this. If I was a statistician, I would be very, very happy with this, but that's not what we're doing. This thing told us a cubic function fits it. Quadratic function fits the points they gave us really well, because the closer to 1 you are, or -1, The closer you are to 1 or -1, the better the fit is on the points. And if I were to graph this right now, that's a pretty awesome fit. It missed these two, but not by much at all. However, we're supposed to get a perfect fit because we got perfect differences the third time around. So this thing back here on the home screen, this tells me I got a great fit. Also tells me it's not perfect. So do it again. Go stat, calc, cube reg. Let's see what happens with a cubic function. We'll do the list 1, list 2, and bars, y bars, function. I'm going to put mine in y2 this time because I want to keep them both. And hit enter. And that's a perfect fit. So we choose this one. If I were to graph now, if I were to hit the graph now, I'm going to come back to the home screen in just a minute. If I were to hit graph right now, here's my quadratic. There's my cubic. Wow. Even the cube didn't fill in these gaps entirely. It's another pixel crisis for our poor calculator. But that piece of the cube graph and that quadratic that I drew through it are practically the same through these points. Now, if you were to widen out your window, you can see that they deviate quite a bit later. So if I were to let my x's go out to 30, maybe, by 5s, and my y's go up to 300 by 50s. There's the quadratic. There's the cube, and they start to deviate there, you know. But for down here where the points are, both of them are really good, but the cube's a little better. So if we go back to our home screen where we got that and we found it was a perfect fit, now we have to interpret this. Do you guys remember from grade school what this corresponds to for value? The 0.3 repeated is, does anybody remember this one? It's 1/6. And if you can't remember it, because I imagine if you do this on Big Ideas Math, they're going to require you to put fractions here, and your calculator only gives you decimals. Here's what you can do. You can type in 0.1 and just put a whole bunch of 6s there. And hit enter. And then ask it to math, enter, enter. That's the way you can get it out of there. You following me there? Yeah.
How do you get back to that screen from the graph? You put second what?
You can't. So we're not on our calculators. You go second entry, second entry, second entry until you get to here and have it refigure it. Second entry is the upper left, lower right. You just keep hitting it until you get back to the one you want to calculate. So now we hit enter and it brings those back. So now that we know what 0.16 repeated is, we can write the equation of this perfect fit. And it is y equals, oh, by the way, it's also in your y equals screen. If you go to y equals, it's also sitting right there. That way you can get back to the details if you want. I'm going to go back to my home screen and show you how we use this. It says it's of this form right here, ax cubed plus bx squared plus cx plus d, and here's your a, b, c, and d. So we write y equals 1/6 x cubed. 0.5 is what? 1/2. X squared. 0.3 repeated is 1/3. And there is no d, it's 0. We don't bother to write it. So that polynomial right there fit that data best. Y'all see how it goes? So if you're doing this and they ask you to find finite differences and find a perfect fit, and you get an r squared value that's 0.99 or point something other than 1, then go the next higher value up. Okay. All right, that was fun. One more thing. Example 3. I like example 3 better than anything else because you will never, or only in a math class, where you get data that's perfect. Which is another reason I think it's silly. If you're going to use mathematics to get something done, then this common difference thing goes out the window because you never get perfect data when you're collecting data from an experiment. And that's what we're going to deal with now. Here's the deal. The table that we're going to be dealing with. The table shows the total U.S. biomass energy consumption. Well, what's biomass energy consumption? Any idea? You guys are going to find this very gross. But one of the best biomass energies we have that we recover is propane and methane. Those are highly flammable gases that you can put in tanks. And we use propane. It's derived from things not quite as gross as I'm going to tell you. But methane is derived from the rising gases off of a big pool of sewage. Yes. After you put that stuff in the toilet and it ends up in the sewage part of the treatment plant of your city, they skim off gases, purify it, put it in cans. Yeah. It is gross, but it's pretty cool that even that kind of crap you can get energy out of. I do this
Basically,
crap.
take a wire to a sewage.
Yeah,
and just-
yeah. It's not quite that bad, because they have to do some processing of it before it becomes reliable and controllable flame. You can't, this is not, yeah. Now, listen, I know this happens because I used to do the ski club here, and it happened on the way home. We actually had to put a fire out. You know how it is, the back of the bus, all riding home, dark at night, somebody's got a lighter, somebody farts. His pants caught fire. Yeah. We had to put a coat over him. He didn't get burned, but he was feeling pretty stupid. Yeah, you can get that to light, honestly. Okay, I wouldn't recommend it. I just want to burn your butt. Okay.
Did he get in trouble?
Oh yeah, he sure did.
Who's this?
What's that?
Who was this?
I was before the turn of the millennium. That's how old I am. I was running ski club in the late 90s, and that was sometime I can't remember. But anyway, I'm just saying that that's what we call bioenergy, biomass energy. That's not the only thing. How many of you got a compost pile on your place when you have composted before? Has anybody ever told you to go out and turn the compost?
Yeah.
With a like a big, it's not a pitchfork, but it's like a leaf, like a hay rake kind of thing. Have you ever done that?
Yeah.
I've had to do that before too. It smells terrible.
Yeah.
But when you turn that over, it is hot in there. It's coming off of that. And sometimes if it gets dry enough before the heat dissipates, it'll start a fire. Haystacks that are not in bales, people just put the hay up there and tromp it down, those can start on fire pretty easy because inside those stacks, it's decaying and all those little microbes and stuff are doing work, and the energy that's put off from that gets hot. It's really hot. It's enough to start on fire. And so there's energy that you can get from all sorts of dead, decomposing things or crap. Okay? So that's what biomass is. And that picture that you're looking at right there is a whole bunch of wood chips piled up that they're gleaning the energy, the heat energy off of it to use. There's all sorts of things that biomass can be used and get energy out of. So the U.S. biomass energy consumption Y in trillions of BTUs, that's what that's pronounced, British thermal units. Again, we're stuck in the English way of measuring things. It's called the calorie in the metric system. British thermal units in a year T, where T corresponds with the year 2001. Find a polynomial model for the data and use the model to estimate the total U.S. biomass energy consumption in 2013. So the data goes up to 12. Can you see that? See number 12, that's going to be 2012 since 1 was 2001. You with me there? And so we're only going to predict one more year into the future using this. Okay, so start entering the data. Stat. All right, check to make sure your lists are the same length and that your second column has 4-digit numbers in it. Make sure you don't get any decimals inserted or miss a keystroke or something. Mine are all 4. At least that's a quick check to see. Okay, now we have to build a window. What do we let our x's range from and to?
0 to 13.
I'm gonna go 0 to 15, just so I can clearly see my 13 when I'm ready, okay? I'll go by 2s. How about the y's?
2,500, 4,500.
Did you scan through there, the very smallest one, is that the 26, 22? Yep. Nothing else is smaller? Okay, so what, 2,500? That's what I'm gonna do. What's the biggest one?
44.
Yeah, is it the 4421? You see that?
45.
I think I'll go to like 4,700, just to give myself a little gap. And 25 to 47 by hundreds is still quite a bit, so I'm gonna count by 200s. Okay, once we design a window, we go where? Y equals, and clear out the junk we had from the last problem and make sure the plot's on. And then graph, and this is what our points look like. Okay, you might look at that and go, I don't know what fits that. Well, here's how you tell. You see how we might have just a really shallow, but a little bit of a bend right here? Comes up like that. That's what I call a turning point, sort of. I mean, it's bending, that's 1. 2, right there, very clear, 2. And remember, a polynomial of degree n has at most n minus 1 turning points. I don't think this looks quadratic. It does to there. And then I suppose we could get a curve to go through there like that. So, I don't know, it looks cubic to me, but we can compare them pretty easily. Here's what we do. We go stat, calc. What do you want to try first, the quadratic or the cubic, to see which one fits best?
Cubic.
Did it tell us to do a cube? Or did it just say find a curve that fits?
Find a polynomial model for that.
Okay, so find a polynomial. You want to try the cube first? Okay, so do the cube and put the information in. List 1, list 2, bars, y bars, function, y1 again, go. Whoa, that's a nice fit. Let's see what it looks like. Pretty close to most of those points. Looks pretty good. I want you to also put a quadratic one in though. So I want you to do that, calc, and then down to quadratic and do it as well and see how well it fits. Put it in Y2. Make sure you put it in Y2 or it'll overwrite Y1.
How do you do
Not-
that? Put it in the Y2.
What's that? How do you put it in Y2?
Yeah.
When you do on the home screen, when you do this quad reg, I'm gonna bring it back up. When you get to there, oh wait, not to there. Let me
Because
clear
ours
mine.
is
Let me just clear
different.
mine. You go stat, calc, quad reg, and then you do your list 1 and list 2, which you probably don't have to do with your operating system. Then you go vars, and then y vars, and then function. And when you get to this list, choose Y2 instead.
Mine doesn't have.
Choose function. You choose function. And then it goes Y2 and it stores books. Yeah, so right after function, if you choose it. Okay, so we hit enter and we get another really good fit, but not quite as good as our cube fit, right? Okay, let's see what that looks like. Okay, graph, and it'll graph them both. There's your cube. Here's the quad. Boy, they deviate in a big fat hurry. They get far apart right there. They were both pretty good fits. The cube was slightly better. Which one do you think is a better predictor of what's actually going to happen with biomass usage, biomass fuel usage? You think it's going to go down? You do? Because that's what the data says? Because we had a better fit with the cube? Me personally, I honestly think it's going to go up. I think this was either bad data collection or an anomaly, because the trend for all the other points was up, 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 and that one dropped. I would think that that would be an anomaly and that this was probably a better predictor, because people are becoming more and more environmentally conscious, and biomass is something that's it's not easy to get, but it's more environmentally friendly because they're using stuff that's going to be thrown away anyway. You know what I mean? People are getting to where they're being a little bit more like that. I'm not proposing one way or the other, but I'm just saying I This is what we call an outlier. I think this is probably a better one if you're actually doing the statistics on this. Now, that's not what the author of the book intends for us to do. He says, use a model to estimate the U.S. total biomass energy consumption. It says, and then he goes down here, he goes step 1, step 2, step 3, he says cube fits better, is what he's saying. And it does, it fits better. And so we're going to use the cube to make the prediction because it was a better fit. That does not necessarily mean it's statistically the right thing to do. So here's how you check it. You go second, calc, a value, and the first one it will go to is the first one that was listed. So it's going to go to the cube one, which is the one we did first. X equals what? 13. And it goes to the cube one and predicts this. And this is the answer to the question. And you should answer the question with the same degree of accuracy that the data was given. You'll notice the data had no decimals. So you would answer 3485. I'm sorry, 4385. Because that's how accurate the data was given to the nearest whole number. Okay, now let's see what that would be, that very, very same number. All you have to do is hit the down arrow, see what that would be quadratically. See, I think this is more likely. Me personally, knowing green energy consumption as time rolls along. Okay, so here's a moral of the story. Even though the quadratic didn't fit as well, it still fit really well. And in the context of what's going on, I feel like it was a better predictor. But the author of the book wants you to find the one that fits best and use that for a predictor, which isn't always reality. Are you with me? Sometimes, folks, and I'm here to tell you this, any set of points, I don't care what they are, if it doesn't fit perfectly with the quad, it will fit better with the cube. And if it doesn't fit perfectly with the cube, it will fit better with the quadratic. I mean, a quartic. And if a quartic doesn't fit, it'll fit better with a quintic. The higher that you go, the more it's allowed to turn and pick up all the points as it goes along. It's always more accurate the higher you go. But what you've got to think of is, I don't really want to report a quintic to make predictions because my quintic is heading down when I know this thing's going up. And I want to use the quartic instead. So you have to think about things like that. And a really good fit, the best fit doesn't necessarily mean the best equation. Okay? So I'm just trying to tell you about that. When you actually take a statistics class, you're not always looking for the best fit. It's nice to compare them. By the way, the cutoff in statistics for a good fit, a good fit, and a sort of good fit, this number 0.7, I think it's 0.78. If it's 0.77 or less, it's not a great fit. But anything from 0.78 up to 1 is a really good fit. So we got some great fits here, even with the quadratic. And it's got a lower power, which means it's easier to use because it doesn't have so much stuff in it, and it's a great fit. The cubic also took a dive. It's coming down. I don't think that's pretty cool. All right, enough discussion with that. All you're going to be doing today is what I had you practice, writing equations with a certain number of points, doing the stupid little common differences until you can make a prediction on what you're going to fit. I mean, you got to do that, practice that. And also fitting real live data. So here it is. It's not very much. It's number 2, 3 to 15 odd, and 23 at the shortest one. But I did do a lot of talking in that connector, so you haven't got a lot of time. Sorry. Shouldn't take too long to finish. Lab's open until 7 tonight.